So hello everybody, welcome to my talk. I'm going to be talking about renewable energy today, specifically more focusing on wind. And doubtless you've heard in the media about wind power going into the national grid and all of the pros and cons for that. I'm going to park all of the pros and cons today and just tell you about the statistics behind it. Okay. So the aims for my talk today is I'm going to describe generally a bit about what the problems are in the area. Okay. I'm then going to give you some examples of where statistics is used in other areas of energy, not just the wind that I'm talking about today. I'm then giving an overview of a specific area that I've recently developed that's still ongoing, so forgive me for not necessarily having the end of the story yet. And hopefully you'll learn something tonight, generally. So all of the work that I'm presenting today is joint. So generally as a statistician, you're not just sat there working in an office on your own. You do actually have to collaborate with a wide range of people. These here are just my statistical collaborators. We obviously work with lots of other people like engineers, companies, energy companies especially, and generally just a wide range of non-statisticians. So the reason why I generally got into statistics was because I couldn't really pick one specific area that I wanted to essentially do for the rest of my life. So I thought, well, with statistics, you actually get to look at lots of different areas whilst being based in statistics. So generally in my career, energy I've been working on for the last 5 years now, but I've also worked on other areas like linguistics, law, generally just lots of different places. I'm trying to think of them now. Okay. So obviously it's a very collaborative, so thanks to everybody, especially Idris, Stan and Guy for some slides. So we're going to say what happens now. So now we don't have much wind penetration into the national grid. So how does the state of play look now? So generally speaking, you've got generation places. So these might be power plants, wind farms, solar on your house, anything like that. And all of that energy that's created goes into the national grid. And then the national grid has to balance supply and demand. So all of this energy is going in. It has to either be used or stored at that time point. And you've got lots of customers in their houses that are wanting energy immediately. Electricity, I'm specifically talking about here. And so what we have is we have grid operators. So these are the people who actually manage the national grid, and they're sat there and it's their job to make sure that demand and supply are matched. Okay? And this is on a minute by minute and even second by second basis. So generally speaking, the demand side of it is pretty well understood. We're pretty predictable as human beings. And typically you're talking about 25 gigawatts overnight, so that's when most people are asleep and there's no manufacturing generally going on, up to about 50 gigawatts or more during the day, so that's with manufacturing taking up quite a large proportion of that. And this demand may be subject to sudden fluctuations of up to about 2 gigawatts. And so typically, a standard example for that is when you see the credits of EastEnders or another popular programme, everybody will get up and they'll go put their kettle on. And when they do that, that can actually create up to a 2 gigawatt surge in electricity needed at that specific time. So obviously if you're somebody planning, trying to get supply and demand up, and you've got these peaks and these troughs and these sudden fluctuations, you obviously have to manage that fairly consistently. So on the other side, traditional supply is also quite well understood. There's contracts for minimal supply for each of the power plants, and generally they have to send predictions of what they're going to generate when. So it's quite easy to sort of see on a minute by minute basis what the supply is going to look like in the UK. The problem is, if something happens that's not predicted, it does take time to change the amount of supply that we're getting from the traditional plants, sort of the nuclear, the coal and the gas. So they take time to turn on or increase in generation, and this can be anything from a couple of hours to actually days to change the output that they're giving. So typically what's used at the moment is hydroelectricity is used to cover this gap. So when you do have that spike, you will see that Norvig, which is one of the biggest hydroelectric plant in the UK, will be given the signal to open the floodgates, and then the water will come down, and that will cover that 2 gigawatt sort of supply-demand mismatch. Okay. And typically as well, if you've got a failure in the system, so say you've got this big network of all the grids and one of your nodes goes down, that can create up to a 2 gigawatt loss as well. So that is also when we use the hydroelectric plants as well to sort of stop gap. And so this hydroelectricity here, especially with Norvig, which is in North Wales in Snowdon National Park. So it's the largest one in the UK. It's got a capacity of about 9 gigawatt hours. And when you open the floodgates, you get about 1.8 gigawatts coming through as the water comes through. So that can sort of stop this supply demand of up to 2 gigawatt gap there. And so what we do then is that water obviously rushes down. That can sort of feed the gap that's missing. But then when that's empty, obviously that needs to be filled up again. So overnight, when we have oversupply, then we pump the water back up to the top, and then it's ready for the next day. Okay. So that's typically how it's done. This is a map here of the total supply for the Great Britain. And as you can see, you've got those cycles in, so the yearly cycles of winter to summer, that's a big sort of smiley face that you get going on, and the little bits where you can see the peaks more often, that's sort of the weekly variation. So where you've got the large bits, that's during the week, and the weekends are the smaller ones. And then if I zoomed in even more, you'd be able to see the daily variation that goes on. And so this bit here, this is a red line, this is nuclear power. So the nuclear power is pretty much constant across time. You have a sort of a baseline output from nuclear power. And so this is the one that makes up sort of the baseline. And then we have coal power here on top, which has the same cyclic sort of effect going on that you see in the total generation. And so this is sort of the main makeup of the supply in the UK. And then we have other things like oil and other things like that sort of make up the stopgaps because they're more expensive to run. And then we have wind here at the bottom. So as you can see, it's the smallest of the generation, but in recent years we have been getting more wind power into the system, and this is causing some problems because obviously if you're expecting wind power to be there, and so you're sort of counting on that for your supply, and then it's not, that means that you've got this gap that has to be plugged. And you can't plug that gap by using the traditional methods because they take time to turn on and change the generation of the electricity. And we can't rely on the hydroelectricity because that's already being used to quite an efficient capacity. It's very expensive to create more hydroelectric plants because you have to find large enough reservoirs and there's time taken to build it. So the question now becomes, how do we actually bring in this wind energy? This is essentially renewable energy, cleaner energy into our system, but not have the risk of blackouts or oversupply, because there's penalties for oversupply as well as undersupply. Okay, so this again is a zoomed in picture of the wind, and you can see how variable it is. So sort of going up and down, it's quite varied, and you'll know yourself when you've been out on a day and suddenly you get a big gust of wind coming through, and then the next second it's disappeared again. So there's lots of problems like that we have to deal with. Just again to show you how variable it is, I've just taken the difference here from one time point to the next, and you can see there's some quite large spikes of negative variation as well as positive variation. So you get these sudden ramp ups of lots of wind, and then also you can have a sudden decrease where you go from having lots of wind to no wind. And this causes problems not only for the actual turbines, which have to deal with this physical battering of a sudden increase and sudden decreases in wind, but it also, for generation purposes, it causes problems there because you've got a sudden input of energy that you maybe weren't planning for, and you have to deal with that in the system. If we've got too much energy going around the system that's not being used, then it can actually break components of the grid, and then obviously that causes its own problems. So generally, hopefully, in that little summary of the grid, I've shown you that power from wind is not on-demand generation, obviously. Integrating larger portions of the wind into grid can create reliability problems, and it's the variability that's the issue, not the actual amount that's generated. So, I mean, if we knew exactly what we were going to generate all the time, like we do with the traditional sources, then there'd be no problem. It doesn't matter whether we've got a small amount or a large amount. If we know what we're actually going to be generating, then we're back to what we know. But it's the variability of the sudden increases, sudden decreases, large periods of times without wind. That's not necessarily in itself a problem, because obviously you can plan for that if you know about it in advance. So the question that I've come to ask is, how can statistics help with these sorts of problems? So I want to start off by just telling you a bit more about other areas of statistics and other things that people have been doing in a more general overview. So broadly, you can have 3 different areas that I see it as to where statistics can help. So we've got system level problems. So things like how much energy will we need tomorrow at a specific time, and what makeup is that energy going to be, you know, from nuclear, coal and wind and solar and things like that. There's the investment side, so where should I put my wind turbine? How many wind turbines should I have? Also, if you're a person who's investing in a portfolio of things, you've then got, you know, how much should I invest in each different energy brand and the different sites across the UK. Okay. From the operations side, so in the UK we're lucky to be surrounded by a lot of sea. We've got offshore wind turbines, and in that, when they break down, it's not necessarily that you can have a boat ready to be able to go out and fix it, but also that the conditions that are around the site actually allow you to be able to go and fix it immediately. So you then want to know, for maintenance as well, when is the best time to go and be able to fix it, for the safety of your staff and also for cost-wise as well. So in the energy demand side, so you would think, as I've just described it, that we understand energy demand quite well. However, with the advent of people switching providers quite a lot, an individual company doesn't necessarily know what their demand is going to be. So, you know, when you've got more customers because you've got a better pricing system, you've then got high demand, and then you might lose those as other people get more competitive. So you don't actually know what your, as a company, what your demand is going to be. So there's financial penalties for oversupply and also over demand. And there's this paper by Hiran Cho and others this year that can actually model this. And there's actually quite a lot that you've got to take into account, because you've got things like the fact that Monday might be different to a Tuesday, and a weekday is different to a weekend. You know, you've got day and night. You've also got seasonal variations of summer and winter. You've got to take into account that, you know, some autumns are colder than others, like we had this spring. It was very, very cold, so it's an unusually high demand there for the time period. And also there's extra things that you might not think of straight away, such as bank holidays and Christmas and things like that, that although if you've got a pattern for, you know, all the days of the week, those actually are almost separate, and you have to model them separately. So there's quite a lot that you have to take into account when you're doing this sort of modelling. And they've done quite a good paper there to have a look at if you're interested. On the other side of it, the flip side, we've got oil. And obviously oil is our current reserves are going to run out at some point. So oil companies are constantly on the lookout for new oil deposits. And one of the ways they do that is by called sniffing the air. And essentially, if you've got some oil underground, it's releasing gases. And those gases can slowly seep up through the ground to be detected above ground. And so one of the ways that they do this is they have a plane like this with a wide array of sensors on it, and they send it around an area, and then they have to actually detect is the concentrations that they're measuring what they would expect in the area, or is there potentially some sites that have higher concentrations of specific gases that might indicate that there's some oil under the ground. So the key points here is it's actually very small, these emissions. So the changes, we're talking parts per billion, sort of a 1 or 2 parts per billion change in the actual concentration levels. And you've got that amid all of the background emissions that you've got coming out of the air naturally. And so you have to take into account quite a few things, and the flight path as well. If it's coming back on itself, then it might be going through its own fumes and things like that. So there's quite a lot to take into account there as well. So there's a paper there by Bill Hurst and others that's quite good at solving that sort of problem. And as well, I was speaking earlier about repair and maintenance. So this is some work that I did with others previously. So generally speaking, you want to be able to know when the stormy season and non-stormy seasons out at the sea are, so that you can actually schedule your maintenance. This is more for maintenance, and you want to be able to know these time points will be changing every year. And there's a plot there just to see what sort of data we're looking at. So you can sort of see when there's a burst of variability, that's when there's a storm season going through, and it's when there's not much variability, that's the calmer seasons. And so you can sort of see by eye there, I'm sure if I asked everybody in the audience to say when was the start and the end of those stormy and non-stormy seasons, you'd all come up with very, very different answers. And so we translated this into a change point problem, and that was published recently in the Electronic Journal of Statistics. And from the investment side now, so this is more getting onto economics and things. So you've got several potential sites where you might want to place your wind turbine, and you've got access to a small amount of wind data from those sites. You might have put up sensors at each site, maybe for a short period of, say, 6 months, and that would be quite high quality data. And you'll also have access to Met Office data, but they're from fixed locations that might not be near your potential sites. Obviously, you've got the topology of the sites. You might have, if the wind comes in from the north, you can't actually, it won't actually go into the turbines because you might be in a valley, or there might be some other obstruction. So generally speaking, you want to be able to almost predict how much wind you're going to be able to get from that site in the future. That's essentially what it boils down to, as to why people tend to make decisions of one wind site over another. Obviously, there are other issues such as costs and economics and the area of how open they are to having wind turbines. But generally, from the statistical point of view, it's how much energy are we going to be getting. And also, if you're a portfolio manager, you might want to invest in different sites that might be more secure or more volatile in terms of what sort of energy profile they're producing. And so it's another question that was answered recently by Hunt and Nason in the Wind Engineering Journal. So generally speaking, I just wanted to give you a flavour of some of the different questions that statisticians are asking in the energy industry. So now I'm going to talk about a project that I've been working on. So this is about wind power prediction, and I'll give you a bit more detail on what we're doing. So in the shorter term, we want to predict wind power because the owners of the wind farms actually need to be able to sell that power. And so they need to say, for example, 24 hours in advance, how much they're going to be generating. And they will sell that much amount of energy. If they then don't make that amount of energy, they've got severe financial penalties. If they make more than that amount of energy, they've then got this amount of energy that hasn't been sold that essentially goes cheaply. Okay? So from their point of view, they need to optimise how much they're actually going to be able to predict to be able to make the most amount of money from their wind farm. Equally, they're giving predictions to the grid, and they're going to be able to balance supply and demand based on those predictions that are coming through. And so those are more ongoing predictions, maybe sort of every few minutes to every hour. Okay. And in the long term, you want to be able to schedule maintenance in periods of low winds. And for investment as well, you need to know how much, as I was saying before, how much energy you're going to be able to produce over, say, the next year. So generally speaking, if you think about predicting the wind, you might think, okay, well, the wind where I am now might be very similar to the wind down the road, obviously. A bit further afield, maybe the next town over. Might be similar to Preston, if the wind's going in that direction. When the wind changes direction, it might be similar to a town the other way. Okay? So obviously there's a time delay there in the time it takes the weather system to get from where you've measured it to where you currently are. And there's also other things like temperature and other environmental conditions that can actually affect how much wind you're getting, okay, at a specific site. What's more important is, as I was saying, if the wind direction changes, then that suddenly changes the relationship between the other sites where you have data and where you're wanting to predict. So all of these relationships are constantly changing. You know, if temperature is high, it may be, you know, more influential over the wind power that you're getting, and that might be the case in June, but then when it's warmer in the winter, it might be a different sort of relationship that's going on. So because these relationships are constantly changing, it's very, very hard to try and actually predict the wind using all of these different things. So generally speaking, this is a map of the UK. If I was going to site a wind turbine in the middle of England, whereabouts do you think might be good for the data to come from? Anyone have any ideas? What would you use to predict the wind in the middle of England? Anyone? No? Basically anything. And any sort of data would probably help you in this problem. I could have information all the way up in Scotland, and you know, if the wind was coming from that direction, then that would probably help me. Okay? Some data is always better than nothing, typically speaking. And generally, you know, any sort of data that I can get from anywhere around the UK is probably going to help me. Okay? But as I said, because these relationships are constantly changing, it might help me at one time point, but then as soon as I'm a few hours later, it will be of no use at all. So generally, you want data from all over to be able to actually predict in a specific location. If that data exists, obviously. So say, for example, I was asking one of you to predict what's going to happen next in this series. Does anybody want to take a guess? Are we on the up or on the down? Up, yeah? It's going to go up, and then down again, and then up again. So what you've essentially done in your head is you've said, okay, I'm going to fit this sort of curve to the data. And you've done that in your head just randomly. Okay? This actually takes quite a lot for statisticians to do to try and get the exact model that would fit this data. And that's because when you're looking at that data, you can see that it's a bit noisy, but your mind's eye can actually remove quite a lot of that noise naturally and see the patterns. Generally, humans are very good at seeing patterns when there are not patterns. So when there is a pattern, we're quite good at picking it up. Okay. How about if we've got something else going on? Okay. Can anybody predict what might happen here? No? Looks a bit like it's changing, doesn't it? So we've got a lower bit at the beginning, and then we're going into something that looks a bit more stable. But if I actually give you another series, okay, and say this might be related to the series that we've already got, what we can do is we can actually say, okay, well, I know that this is constant, so I can remove that effect. And if we remove that effect, this is what we get. So what do people think? What are we going to predict now? Yep, it's generally going up, okay? But from the original picture, you wouldn't be able to tell that, okay? So this is how we actually use other information that we have, say for example, wind at other locations and things like that, to actually get the actual answer of the straight line. Okay? So you can sort of see how out of nothing, suddenly you take into account what's going on in another variable and the picture becomes clearer. So similar here, this one's a bit more complicated. Can anybody maybe see what's going on here? No? This is the sort of thing that is harder for humans to see, because essentially our next time point only depends on the 2 time points previously. So in all of the other examples you had a trend, something that was going on actually in the mean of the distribution that was changing over time. Here, what's actually happening is that there's no other variables going on. It's just that where I am now just depends on where I was in the previous 2 time points. And then obviously you've got some noise added onto that. So essentially we're saying here, I'm heavily dependent, so 0.7 probability, on the last time point, and then I'm a little bit dependent on the time point before that. So you can sort of see that by when you're going up, you tend to sort of stay going up a little bit and for the next couple of time steps, but then when you've gone down, you go down a little bit. It sort of clumps together the time points and sort of moves slowly rather than jutting up and down all the time. Okay. And so the way that we can actually find that out in statistics is using a function called the partial autocorrelation function. And that basically looks at, instead of looking at the correlation between one time series and another, so how alike they are at any time point, what we're actually doing is we're saying how alike is it to itself. Okay? And specifically with the partial autocorrelation function is it saying I'm at this time point, how alike am I to say 2 time points ago given 1 time point ago? So say I know about time point now and the time point previously, how much extra information does the 2 time steps ago give me? And so this is what this is doing here. So the first point is basically saying I just have my point now. Does the next time point give me any extra information? And because that's a big spike, we say yes, it does. And then we say, given those 2 points, what is 2 time points ago? And that's our second spike there, which is also above, outside of the dotted lines. And then we go to 3 time points ago, and this is when we've actually got smaller and smaller coefficients there. Because those blue lines that we've got there are our confidence. And essentially, if you've got random noise going on, so where you can't predict it, it should stay between those 2 blue lines. So essentially, this tells us that we only need the last 2 time points to actually predict this series. And that's why we've got, and then you sort of estimate the coefficients of that, and that's how you get to the formula at the bottom. Okay. So it's a bit of magic, I think, because you can't actually see it like you can with the other examples that I was showing, but there is a translation behind it as to how statistically you can actually tell that it's 2 and not 3, 4, 5, etc. But what if this model was changing over time? So no matter where you were in that time sequence, you always knew that you only needed to know the last 2 coefficients and you were okay. And those coefficients, the 0.7 and 0.2, were constant depending on regardless of where you were in time. So if it's changing over time, those parameters might be changing, but also, say now, I might only need 2 time points to go, but at the next step in time, I might need 3 or 5 or 10 or 1. And so when things are changing over time like that, it suddenly becomes very much more complicated. So how do we actually cope with this extra complication of when things are changing over time? So some people out there, and quite a lot of people out there, just ignore it. And they say, oh, it's changing over time. We don't mind. We'll just pretend it's not. And so there's actually quite a big danger there. So if we actually look at using the whole of the series to estimate what's going on and do a forecast, we get this red line here. If we just use the last 30 observations in a series, then we get the blue line. And you might say, oh, that's not too much different. But remember, we're not looking at the actual values, we're looking at the confidence intervals. And so here, because we've got less data in the blue line, we have a wider confidence interval. So we've got less information, so we're not as certain about what's going on. And for both of those, with what's gone on recently, you might think, oh, are they a bit overconfident? There's actually quite a few time points in the recent past that would fall outside of those confidence levels. And because you're assuming things are staying constant over time when they're not, you can actually be overconfident far too often. And so you think you're being, for example, 95% confident about something, but you might actually be closer to, 60, 50, 40% confident. Okay. And there's the added bonus in this of, well, say you want to assume that things are constant over time, and you think, oh, well, actually, I know it's not constant over the entire time, but I think it's constant over the recent past. How many observations do you actually use for that? You've then got the trade-off between having, you want a lot of information to be able to estimate it accurately, but you want a small amount of information because you don't know that things are actually staying constant. So can we do any better than this? And generally, I would say yes. So instead of wrongly ignoring the fact that things are changing, the school of thought that I and a few of my colleagues come from is that things don't generally tend to change very suddenly. So we say that things change slowly over time. And when we do this, it's called locally stationary. And stationary, obviously, doesn't change over time. And so I've got an example here of something that on the left there that obviously changes over time. But if we actually zoom in far enough into the series, like we have on the right here, it actually looks like it might stay constant over time in terms of what's happening on in the series. And that's what we call locally stationary. It's that if you are looking at the whole thing, then you'd say, no, that's not staying stationary over time. But if you zoom in enough, and here I've got 600 observations, but I might need to zoom in a bit more on some series and a bit less on others, then you would say that if I zoom in enough, you can actually say that things are constant over time. And so that's the school of thought that I come from. And so here's an example of this sort of series. So we have what we had before, where you have to go 2 observations into the past. And here I'm saying that the coefficient that I've got before that, so for example my 0.7 and 0.2 earlier, is changing over time. So we're going to start with it at plus 0.6, and we're going to change it over the time series linearly, so just in a straight line, down to minus 0.6. And this is what it looks like. So in the beginning you can see there's a bit more clumping together, and then you go towards randomness, and then there's a bit more negativity of where you're 1 time point, and then 2 time points later you get the opposite of that. So this is what we had before. This is our partial autocorrelation function. So that's how we knew that it was 2 time points before, because it was 2 above the series. But now, rather than just having this as the same over time, we've obviously got each of these lines here is going to be across time. So we're going to have lots of different graphs for all of the different all of the different lags here. So a lag is like lag 1 would be the relationship of now with just the time point before. Okay, and so we can look at that. So this is the lag 1. So that's my relationship of now with the time point before, and this is over time. So you can see it's sort of changing over time slightly, but it's more or less, you know, dotted around 0 there. And then if I'm looking at the time point now from 2 time points ago, taking into account the one in the middle, this goes from, well, it should be 0.6 down to minus 0.6, but obviously there's some random variation coming in with the fact that I'm using a simulation rather than the specific model. But you can clearly see that we've sort of got a linear line there, a line there going from there about 0.5 to about minus 0.4. So you can sort of see it slowly changing over time. And so this is how we can incorporate the fact that things aren't constant into our models. So if we go back to forecasting now, and we're going to apply the same thing, we're essentially going to be using this, what we call local partial autocorrelation function, to decide how far into the past we're actually going to use to predict the future. And so we do that here. So this is a very bursty sort of on-off sort of signal. And where we're going to predict is at the end of this data, so we're just about to go into another burst. And the forecasting takes this into account with our wider confidence levels here, anticipating that we're going to go into this other burst. So that's looking pretty good. Whereas a conventional series here, if you assume stationarity, will likely, if you do it over a shorter time period, say I'm only going to use the last 30 observations, would be quite tight on the confidence intervals, because the last 30, you know, it's small variation coming through. Whereas we know, because we can look at this, the whole series and take into account what's gone on in the past in a sort of adaptive manner, that it's going to go bursty again. So we have that sort of uncertainty into our forecast. And equally here, so before it was quite regular in its sort of pulsating. Here it's irregular. And so we still get that same sort of wide confidence band coming through, because we're not sure what's going to happen. So just back to the wind forecasting now, just briefly. So we've got some data here. It's called MIDAS, and essentially it's lots of different stations all over the UK. You need to thank the British Atmospheric Data Centre and the UK Met Office for this data. We've got lots of sites all over the UK, all that are recording the wind at that specific site over time. Okay, I'm going to pick 2 out of here. There's Cardinham and Shoeburyness. There are 2 locations there. Okay. So this is Cardinham on the left-hand side here. So you can see the sort of periods where there's no wind, that's the constant at the bottom, and you've got periods where you're actually rapidly increasing how much and rapidly decreasing how much wind you have. So if we take the first difference there, so that's just a difference of 1 time point from the next, we get this picture on the right here. And you can clearly see that there are bursts of higher variability and smaller variability within that data. So we might say that the properties are changing over time. Okay. So if we apply our method to that, so the true here is in green, the green squares, diamonds. The red is our method, so we've got the open circles are the actual point estimates and the crosses are the confidence intervals. And then the black one is what happens if you assume that things are constant over time. Okay? So you can see here that more or less that our confidence intervals are slightly tighter than the other one, but we do pretty much well on these. There's not too much difference between them. And you'll see that our confidence intervals are sort of slowly actually starting to narrow there, presumably because the data is potentially going into a period of lower volatility. And then here, this is a Shoeburyness. And here it's clear that our actual confidence intervals are tighter than assuming the stationary. So if you're a grid operator here, you could actually say that I actually are more confident about how much wind I'm going to be getting out. I know these are 95% confidence intervals. I know it's 95% of the time it's going to be between these two values. Okay, and that will be better for me for scheduling how much standard generation that I need, and ultimately trying to get away from traditional resources onto renewable resources. So that's just a little bit of a taster of the sort of thing that I'm doing at the moment. As I said, it's not the end of the story. This is ongoing work. But hopefully this evening you've learned something a bit about how the UK grid works and some of the problems of introducing renewable energy, and hopefully some statistics too. We've seen how statistics are starting to try to answer some of the problems coming from the energy industry. We are a little bit behind on the curve there. And we've delved a bit more deeply into forecasting series that change over time and the reasons why we might need to take into account that things change over time. As I said, this is work in progress and we can still do better in our forecasts. But hopefully you've learned something today. Thank you very much.